Alrighty. Good morning, good evening, good afternoon, or whatever time you are watching this video. Um, Thank you for tuning in. Today is the last lecture with new content for our class, and today we're going to be covering what is in Chapter 9 of Dr. Svedkov's notes, which is called Reactor Analysis, but it's more about putting together everything that we've talked about so far and giving kind of like an overview of the state of nuclear power in the United States and also in the world. So yeah, let's get into it. Just kidding. Before we get into it, just wanted to remind us about what the rest of our semester looks like. Today is Wednesday, the 29th. So we're doing our final lecture asynchronously. Um, After you watch this lecture, go onto Canvas under modules, and you should find our quiz number 10. Quiz number 10 is out of 50 points instead of out of 25 points. And it covers what we talked about in the last couple of lectures, as well as a couple questions over today's class. So make sure that you complete that by the end of the day. Um, and yeah, hopefully that one goes well for you. When we come back to class on Monday, that will be our last class before the final. Um, the review for our final exam and the formula sheet for our final exam have already been posted. You can find those on our Google Drive. Make sure that you are staying on top of those things. Before you come to class on the 3rd, you should have already went through the review, at least read through it. A lot of the review is based on what we've done in exam one and exam two, because there's only a couple new things that we've talked about since exam two. So if you did good reviewing for exams one and two, then you kind of already got your review for that part of the class. And for the 3rd, you would mostly be wanting to focus on, for new stuff, what we've covered since exam two, which would be production destruction equations and the buildup of certain important isotopes like xenon and samarium. So on the 3rd, because we've covered so much in this class, like Dr. Svedkov's notes is like 200 or 300 pages worth of material that we've covered. I can't cover all of that in one review session. I don't even think it would be a good time for me to try to review that for the entire session because you've already seen a lot of it. So my feeling on this final exam review day would be I'm going to talk maybe for 20 to 30 minutes about what the final exam is going to look like and cover just some key concepts. And the rest of that class time is going to be for you guys to be able to ask questions based on what you have, questions that you have about the final exam, questions that you have based on the previous exams, and questions that you have based on the final project. Um, if a good thing that you would want to do in preparing for the final exam, if you haven't done this already, would be to go back over exams one and two and make sure that you can correctly do all of the problems in exams one and two. If you missed a question on those exams, you should rework them and try to get the right answer. A lot of those answers, for example, if it's like for the power peaking factor of a specific geometry, that's already in, you can find that answer in Dr. Svedkov's notes. If it's about finding the flux magnitude for a certain type of, and when I say a certain type of reactor, I mean one group diffusion theory, bare homogeneous reactor, using one group diffusion theory. So if I asked you to find the flux magnitude for a particular geometry, you could, that answer is already in Dr. Svedkov's notes. So a lot of the answers to these exam questions, they would either be in the notes or they would be in the problem set solutions. So make sure that you can complete those questions that you might have missed on the exam, on exams one and two, because there's a good chance that you might see those again on the final. Um, the final is going to be, you know, like probably 40% exam one, 40% exam two, and then 20% of the new things that we've covered since exam two. So come to class on the 3rd with lots of questions, either about the final exam, about the previous exams, or about the project. Because don't forget that your reactor design project is due Monday, August 3rd at midnight. So if you haven't started that already, you need to start tonight. You need to let me know as soon as questions come up, because questions are going to come up. Don't try to think that you can do this all in one day. It might technically be possible to do it all in one day if you completely understand exactly how to do everything and you've just been procrastinating on it, then it's possible that you could do it in one day. But why run that risk when you have time in advance to do what you think you need to do? And then at that point, if you're right and you can do it all in one day, then just get it done a little early. But if you're wrong, you want to give yourself some buffer time for being able to complete those questions to be able to get the right answer. Because when I'm grading for the final exam, I'm going to be grading for a combination of accuracy in terms of how close is your final configuration to the correct configuration, and within the range of allowed uncertainty for that K effective, like it's K effective of 1 plus or minus 0.003. So technically, if your K effective is within that range, then you would be good. But yeah, basically making sure that you have the right K effective at the right enrichment. And so don't wait till the last minute on the project. Start the project now if you haven't already, and then let me know about any questions that you get as they arise. Because if you're emailing me about questions for this project on the last day of the project, like if it's due at midnight and you're emailing me at like 8 or 9 or 10 o'clock, chances are I'm not going to see that email, and then your question is going to go unanswered. So come to the 3rd class on the 3rd with lots of questions. Um, once the project is due on that day, we will have our normal help session on the 4th. Because the project will be due, you probably would only be asking questions about the final exam. Um, so, you know, technically that project has you will be getting penalized if you turn it in late. So if you got really stuck, you technically could take a point deduction to submit it on Tuesday. You could take a further point deduction to submit it on Wednesday. Um, so technically, I guess on Tuesday, if you were still waiting to turn it in, you could ask stuff about the project, but I was hoping that the Tuesday class would be mostly focused on the final exam. Any last minute questions that you have about the final exam, we can get those answered so that you could be as prepared as possible for that final exam on Wednesday, August 5th. That is going to take the full final exam time, which is 2 hours. We'll be meeting in our normal classroom in the OMB building, and it'll go from 1 p.m. to 3 p.m. So make sure that you are on time for that, and make sure you're prepared. Make sure that you've studied the formula sheet so that you know what formulas you have available to you, and make sure that you went through the exam review so that you know what kinds of questions you might see and what kinds of derivations you might be responsible for. This is just reminding us a little bit more about the final exam. Basically, everything on this slide I kind of talked about on the last slide. Um, Exam is going to look very similar to our previous exams, but it's going to cover everything that we've covered in the class. And that review, you can find that on our Google Drive, as well as the formula sheet. If you haven't already, please do complete your course evaluations for this class. I've enjoyed teaching this class. This is my second time teaching it, and so it's been a pleasure. I recognize that this is a hard class, so I've tried my best to teach it in the way that I would like it to be taught if I was taking this class as an undergraduate. Um, I hope that even though it's a hard class, that you've appreciated at least some aspects of how I've taught the class. So and part of the reason that I'm teaching this class is because I want to be a professor someday, and so your evaluation is very helpful for me in getting good getting some data, some concrete data from my students in terms of things that I'm doing well, or maybe things that I could improve on for the next time that I teach this class or the next time I teach a similar class. So whether you like the class, whether you didn't like the class, I would appreciate your feedback and I would appreciate you taking some time out of your day to complete these course evaluations. So if you have done that, thank you very much. If you haven't done that yet, I would really appreciate it if you did. So, what is nuclear reactor analysis? What have we been doing over this last summer? Um, the main goal is to get a good understanding of how and why nuclear reactors work, how and why they do what they do, and how we can use the principles of nuclear engineering, specifically of nuclear physics, of neutronics, to better understand some of the issues that might come up if we were to decide to build a reactor, and possibly how to mitigate those things too, and also knowing why those things happen. So we've covered a lot in this course. We started talking about different neutron nucleus interactions. We've talked about conceptually what kinds of interactions neutrons have when they are existing in a reactor. We've used those types of interactions like fission and absorption and scattering. And we've used those things to develop conservation statements. Um, we've learned about the properties of different materials, like what are the properties of a fuel? It needs to have a fission cross section. It needs to produce some number of neutrons per fission that's more than one, such that the neutron chain reaction can continue. Um, and putting those two pieces together, knowing about different kinds of materials, knowing about like our moderators, knowing about what kinds of materials make a good moderator, so that if I'm trying to design a critical thermal reactor, then I can pick a good moderator that's going to be able to achieve the level of moderation that I need for my system. And once you know about properties, once you know about different kinds of neutron nucleus interactions, you basically have an understanding of everything that a neutron could do in a reactor. And then we started using that information along with conservation statements to develop neutron distributions in various contexts. We started out with one group diffusion in steady state, finding how neutrons distribute themselves in terms of position in simple reactors of nice geometries like spheres or cylinders or cubes or rectangular parallel pipets. Um, so we learned a lot about how neutrons distribute themselves in space from one group diffusion theory. The next thing that we did is we added energy dependence. We started taking more having more concern about how do neutrons, about the neutron energy spectrum. We started being more careful about realizing that because neutrons have this distribution in energy, that affects our reaction rates. It affects our cross sections because some reactions are more likely at certain energies than others. And we ultimately developed conservation statements that would tell us not only about how neutrons distribute themselves in space, but also how they distribute themselves in energy. And we learned about how energy dependence can be used to determine what our neutron energy distribution would look like in the fast spectrum, where we showed that in the fast spectrum, it looks like the fission spectrum, how in the slowing down region, it looks like 1 over E. And then we talked about how in the thermal range, the energy spectrum looks like the Maxwellian distribution. And then once we did that, we also started talking about time dependence. We used the point reactor kinetics equations were the main model that we used to say, once I have this critical configuration, and then I make some change to that configuration by like adding a control rod or removing a control rod, how that neutron population evolves with time. And we didn't really talk too much about distributions in angle. Um, Technically, if you wanted to learn about that, that's more of like a graduate level focus. That would be involving the neutron transport equation, which is one step above the energy dependent diffusion equation, where it allows you to even have the specificity to say, this is also how our neutrons distribute themselves in terms of angles in our reactor. So if you go to grad school, you can learn more about transport theory, but we mostly focused on position and energy and time. Um, kind of kind of taking a step back, we learned based on this information, we learned about how to compute all these different production and loss rates. Those were what went into finding the neutron distributions. Um, we studied different kinds of reactors. We discussed how to find or what would be critical configurations for various kinds of reactors using one group diffusion theory, using multi-group diffusion theory. Um, and we haven't explicitly really talked too much about other than just saying, like, in terms of energy conversion processes, I think we're all mostly aware that in this class, we've mostly focused on reactors, which is how you can get a nuclear chain reaction to be self-sustaining, to be critical. And that's where the energy is going to be coming from. That's where the energy of a nuclear power plant comes from, is from the reactor. And then your reactor, your nuclear power plant, rather, is a very complex thermodynamic system by which you take your energy from fission and then you do some conversion processes to eventually take that heat energy and convert it into mechanical energy, which then gets converted into electrical energy, which is then how we can power homes and power buildings and use that energy for a useful purpose. So once you put all this together, you can start actually making reactors that can produce power. And so now that we kind of have talked about all these different things, now that we're at a better place to understand how and why nuclear reactors do what they do, we can start better understanding the current nuclear landscape. We can start understanding the newer kinds of designs that are out there that people are trying to bring to market, and we can have some appreciation for why there's increased interest in nuclear power as a form of energy. And so, like, in terms of putting it all together in energy conversion processes, this is kind of like helping us to maybe start to visualize what that would look like. And that we have our core right here. That's where the thermal energy of our system comes from. You usually, pretty much any reactor is going to have some kind of working fluid, which is a fluid, like it might be water if it's a light water reactor. It might be heavy water if it's like a CANDU reactor. It might be some kind of gas like helium if it's a gas-cooled reactor. We also have reactors that use molten salts as their working fluid, but this is just some kind of fluid that is used to absorb or take on the heat from the fission reaction. So like the coolant comes up, it goes through the core. This coolant is cold when it goes into the core. As it passes through the core, the fuel transfers heat to this working fluid. And so as the fluid goes up through the core, it heats up, its temperature changes, its pressure changes, and ultimately, depending on the design, that hot fluid is then either taken to a heat exchanger, or in this design, this is a boiling water reactor, which means that as the coolant goes through the reactor, it actually starts boiling while it's in the reactor, and you have a steam generator that is basically a part of the primary circuit here. And the steam that gets produced then is taken to turn a turbine. So that's converting the thermal energy of your coolant into mechanical energy of a spinning turbine. Once you have this mechanical spinning turbine, that gets connected to a generator, like an electric generator, which uses the rotation of this big metal thing to generate a current. That current, that electrical, that is converting the mechanical energy into electrical energy, and then that electrical energy can go to the grid to power our homes, to power our lights, to power our computers, to charge up our cars if we have an electric car, and so on. So reactors are really cool, and now that we can understand them, we can start talking more about the current energy landscape. Um, you might not have thought too much about, like, I think we take energy for granted, we're in a developed country like the United States, we're used to the electricity just turning on. We flip the light switch and the lights come on. We plug our charger into the wall and then our device charges up. So we kind of take energy for granted, but energy and electricity are like some of the most important commodities that we have. If you lived in a country where you didn't have reliable energy or reliable electricity, it becomes a lot harder to do basic day-to-day things in your life, like cooking food or reading a book. Like if you don't have a light, then you can't read. If you don't have electricity, then it becomes harder to cook. It becomes harder to heat your home or cool your home. It becomes harder to have reliable transportation. Um, if you don't have electricity and you don't have energy, then you don't have internet, you don't have computers, you don't have your TikToks. So like imagine what your life would be like if you didn't have that reliable energy. Um, this figure right here is showing the U.S. primary energy production by the different sources from 1950 to 2023. They use funny British thermal units as the unit of energy here. So if you look at like 1950, in total, were using like 35 quadrillion British thermal units. And today, I mean, this is 2023, but like by the end of 2023, we were using over 100 quadrillion British thermal units per year. So from 1950, it was like 35 to 2023, it's like over 100. So that's like a factor of three increase in how much energy we have been using from 1950 to today. So the amount of energy that we've needed has went up considerably. And the amount of energy that we use is going to continue to go up considerably because of factors that are relating to how our societies are changing. Um, a lot of that is driven by electrification that we are taking, we're in some places, we're shifting more away from the use of burning fossil fuels to using electrified, using electricity instead of using combustion, basically. And so, I mean, sometimes that electricity does come from combustion, but in terms of our energy consumption, we are moving away from like for example, we're moving away from using like heated stoves like that are burning gas to using electric stoves. In terms of our cars, we're moving away from using gasoline cars to using electric cars. So electrification is driving the changes in where our energy is coming from. In terms of our energy consumption, we just have more people. Like as our populations increase, we need more energy. And we are developing technologies that are very energy hungry. So that would be things like data centers are using a lot more energy, which is increasing our demand for energy. And so on this chart, you can kind of also see the different sources of energy and how their share of the mix has changed. The dark blue is coal. And so from like the early 2000s to today, you can see that the amount of coal that we've used has like almost halved. In the early 2000s, it was like around 20 quadrillion British thermal units, and today it's like just over 10. So the amount of coal that we've used has like about halved, but the lighter blue is the natural gas. And so really what you're seeing here is that we've kind of started to replace our coal power plants with natural gas plants. Um, that is actually part of the reason why our emissions aren't as bad as they could be, in the sense that coal is like the worst possible way that you can generate energy from like an environmental perspective and from like a greenhouse gas and air pollution perspective. Coal is very, very dirty. Natural gas still contributes to greenhouse gas emissions. It produces methane, for example. That methane gets released from natural gas. Methane is a potent greenhouse gas, so it contributes to climate change. In combusting methane, you end up putting other things into the atmosphere that have an environmental impact, but comparing natural gas to coal, natural gas is a cleaner source. Even though it's burning, it's still cleaner than coal is. So as we've transitioned from natural gas to coal, it has actually helped lower our emissions, even though we've been consuming a lot more energy from natural gas. Um, Crude oil has kind of ebbed and flowed. It's not too much different uh, from today from where it was, say, like in the early 1970s. Um, if you look at nuclear, we didn't really have nuclear power before around 1960, 1970. We started building out our nuclear power plants over like the 70s and 80s. And then once we got into the 90s, you can see that things mostly stagnated. The height of this little nuclear power bar is, relatively unchanged from like the early 90s to today. Um, and the thing that has changed a lot besides natural gas is renewables. We used to get basically nothing from renewables, and as time has moved forward, the thickness of this green line has continued to increase. So because of trends in where our energy is coming from, um, because of trends in terms of where our energy is coming from, and concerns about what kinds of energies we want to get our sources that we want to get our energy from, our sources of energy have been changing, and also because of demand of energy as a whole, our consumption of energy has been increasing, and there's projections that say that within the next couple of decades, our energy consumption can continue to increase by like over 50%. So, the factors that are driving increases for energy are also some of the factors that are driving hype around nuclear power. In the industry right now, people are talking about like a new nuclear renaissance. There's all these new startup companies that are trying to build and bring new reactor designs to market. Um, there's a lot of buzz around nuclear power. And a lot of that buzz comes from the fact that climate change is putting pressure on fossil fuel generation. We are starting to realize that the places that we get our energy from are impacting the environment, and some people are concerned about that and are taking course in terms of responding to that in different ways. Um, it's also due to just increase in demand for electricity. So this is a picture of Amazon's largest data center complex in Indiana. They have each of these like big buildings is a data center, and so this facility is going to end up having 7 different data centers. It's going to be about 1,200 acres of land that's being used. And in each of these data centers, you have lots and lots of computers that are being ran to do things like train AI data algorithms. And also Amazon does a lot of like services that involve like basically you can rent their computers from them and use it's like called cloud computing, where you are paying them to use their computers. And so this entire facility is mostly just being used for AI training, for cloud compute, and this facility is using 2.2 gigawatts of power per year. And this is all Amazon is partnered with one of the AI companies called Anthropic that runs the Claude AI. And so this is one data center from one company that uses 2.2 gigawatts of power per year. And when we say gigawatts, that's 1,000 megawatts. So like one AP1000, a single AP1000 reactor is 1,000 megawatts. So it has a power output of 1 gigawatt. So this one Amazon facility is using the equivalent of like more than two AP1000s worth of power. Um, and so AI data centers in general, but then the boom with AI is causing the data center build out to expand, which is causing pressures on our electric grid, on our electricity prices. And so people are realizing like we're building these data centers really fast. At the same time, we need to be building more power. And so that part of the reason that nuclear is connected to this is because the companies that are involved with making AI data centers have, at least in the past, signaled that um, they try to make it seem at least like they're environmentally conscious. Like if you look at Nvidia, if you look at AMD, Google, and Meta, all of these companies have made net zero emission pledges where they're saying by this year, our processes are gonna on net produce no greenhouse gases. So if they are to hold true to their pledges, as they build out all of these data centers, they need to be able to do it in a way that doesn't add carbon to the atmosphere, that doesn't produce greenhouse gases. And so, as a result of that, they need clean power. They need power that can run these facilities 24 hours a day, 7 days a week, 365 days a year with basically little to no stoppage time. So, in terms of doing that, they can't really use renewables unless they were to um, have a lot of battery backup power to make sure that these facilities could run even at night, like when there's no sun, or during periods where maybe the wind isn't blowing as strong as it was. So it becomes harder to run these facilities 24/7 if you only use renewables. But if you need your energy to be clean, nuclear is basically one of the only options that you have. So nuclear is kind of almost like the hype for nuclear is kind of like going in tandem with the buzz around these AI data centers. And so in some ways that could be a good thing for our industry if it means that new nuclear power plants actually get built to facilitate the what's going on at these data centers, but also the nuclear power has kind of always had a public perception problem, which has only started to get better. But I don't know if y'all have kind of seen, I don't know what y'all think about data centers, but if you look at like the people who live around these data centers, they're not super happy about this. So, like, hitching our wagon to us, our being like the nuclear community, hitching our wagon to data centers. It sounds good if it means that our power plants get built, but so far none of our power plants, there's no nuclear power plants that are under construction right now to power a data center. So these things are getting built. People around these places are really upset with them. People who don't even live around these things are upset with them because a lot of these companies are straight up like, we're building AI because it's going to take your job. And so I have some concerns about how much nuclear is like being connected with these data centers in terms of if nuclear has a public perception problem and data centers have a public perception problem, and then everyone's saying, well, we're going to power these data centers with nuclear power, then it kind of stands to reason that that could end up coming back to bite us if if people continue to be skeptical about these data centers. Um, so if you think about that one Amazon facility, that's one company with one facility that has this new data center complex that uses 2.2 gigawatts of power. But Amazon isn't the only company in the AI space. They're not the only company building data centers. You take that one facility and then you multiply that by every tech company in the space that's building data centers, every Microsoft facility, every Apple facility, every Google facility, every Meta facility, every XAI facility. All of these companies are needing data centers, and that means that all of those companies are going to be building data centers, and all of those data centers are going to be using a lot of electricity. So even just like if our population wasn't growing, we were still going to end up using a lot more energy and a lot more electricity because of these data centers being built out. So these solid blue lines are projections for how much electricity demand is going to be associated with data center buildouts. Also, the lighter blue line is transportation, and that has to do with the only way electricity comes from transportation is if you're like charging electric cars, or maybe I guess if you're like building like electric buses or like subways that were electric. Um, and so when we talk about electrification of the economy, we're talking about this transition from things that burn like fossil fuels to produce energy to things that just use like electricity from the grid to charge up a battery to then run those machines, or just using electricity from your house to do some process instead of burning a carbon to make that happen. So like gas cars being transitioned to electric cars, gas stoves being switched over to electric stoves, and furnaces being transferred over to heat pipes are some examples of ways that we are electrifying our economy that is reducing our need for burning some kinds of energy, and it's increasing our need for generating electricity to do these things in a different way. So we need energy. We need a lot of energy. Energy is directly related to our standards of living, and we're going to continue to use energy. That's not really going to change. So if we are going to continue to be using energy and we're going to continue to use more energy, then it's a question worth asking, which is where do we get our energy from? And we had kind of seen this on the previous, on like the first slide that showed our projection, how our energy consumption in the US changed from 1950 to 2023. This chart is showing our primary energy consumption by source in the year 2021. So it's easier to see where these pieces of the pie are coming from. As you can see, petroleum and natural gas make up like the lion's share of our energy consumption. Natural gas is pretty much exclusively used for electricity generation. Petroleum is pretty much exclusively used for cars, for cars as well as large mechanical equipment. Like in agriculture, we use a lot of diesel. So diesel powers our farms in terms of like all of the tractors and things like that. Petroleum products also go into like the airline industry. And so we're using petroleum and natural gas are like the biggest things. Coal is a shrinking piece of this pie. The coal was mostly just being replaced by natural gas, and to some extent, it's also coal is kind of going away, and renewables are growing. If you look at what our renewable energy, so right now renewable energy is about 12% nationally. Some states have a lot more renewable energy than others because part of it is location sensitive. Like if you look at these pieces of the renewable energy pie, hydro and wind are the two, I guess, in biofuels, but hydro is kind of tied with biofuels, and so hydro electric power is very location specific. We're kind of tapped out in terms of where we can get our hydroelectric energy from because you need large re water reservoirs and dams and things like that. So that is very much location specific. Geothermal is a tiny piece of the renewable energy pie that is also very location specific. There's only a few places in the country where you can reliably get geothermal energy. And so wind and solar are also kind of similar in that some places are really good for wind and solar. Texas as a state is actually really good for wind and solar because it's very hot and we also get a lot of wind. And so um, where we build renewables is kind of going to depend on where it's feasible to do so. Um, and so, yeah, in general, renewables are increasing. The cost of renewables has been going down. And so some states like Texas actually, if I'm remembering the numbers correctly, Texas actually has the largest amount of energy coming from renewables of any state, even though we're like, that might be surprising to some people that like we in Texas actually get more renewable energy than we get more energy from renewables in Texas than California does. That might be surprising to some people, but that is true, and it's largely because of Texas just being very, very big and having the kind of layout geographically and such that it makes sense for us to do that. And nuclear power is about 8% of the total. And nuclear power is, in terms of like the slice of the pie, hasn't really been changing that much. In the last couple of years, we've turned on a couple new reactors, but we've also been turning reactors off. We've let a lot of reactors kind of they've hit their end of life, and then instead of having their licenses renewed and having them been upgraded to renew for to run for longer periods of time, a lot of our nuclear power plants we've just let them go into decommissioning. So this slice of the pie has kind of mostly stagnated because we're shutting plants down faster than we're building them, but also the plants that we do have, we've been getting better energy extraction from them in the sense that we've done things like we've been running our fuel at higher burnup, which allows us to run our reactors for longer, which allows us to get more energy and more efficiency out of the plants that we have. So things like efficiency upgrades and burnup increases have allowed us to get more use out of the reactors that we have, which has kind of helped the nuclear piece of the pie stagnate. But so as you can see, most of this pie, 32 plus 36 plus 11% is coming from things that are burning of fossil fuels, which are contributing to climate change. If you look at globally how much fossil fuel consumption releases into the atmosphere, it releases 50 billion tons of greenhouse gases every year. 50 billion tons of carbon dioxide, of methane, of water, which is also a greenhouse gas. These are all being dumped right into the atmosphere every year to the tune of 50 billion tons, and that affects the climate. We've known about things like the greenhouse effect for a really long time, and fundamentally, that's mostly like that phenomena, the greenhouse effect isn't in question. We also know that like this is a number that you can track. This is a number that you could predict just based on how much fossil fuels we actually use every year. And so this number is not really in question. And we can also quantify how much carbon and how much greenhouse gases come from natural processes like volcanoes and things like that. And if you look up how much carbon gets emitted from like volcanoes and geo geothermal kinds of activities, um, it's way less than 50 billion tons. So we can pretty reliably quantify how much we are producing. We can decently quantify how much the Earth is releasing, and our number is way bigger than the Earth number. So that is why the scientific consensus in terms of people that like dedicate their lives to studying climate change say that we are causing the net amount of gas emissions, and it's pretty uncontroversial that having more greenhouse gases in our environment causes the average temperature of our environment to increase. And so it's our activities that are driving climate change. And so we should really seriously ask the question of where do we get our energy from? And once we know where we get our energy from and we acknowledge the pros and cons of these different energy sources, the next thing that we should probably ask is where should we get our energy from? Um, in terms of like the reason that I got interested in nuclear power in the first place is because it is a way to produce clean energy clean energy at large scale, baseload power, which means that it can run pretty much reliably 24 hours a day, 7 days a week with very little off time. And the running of these nuclear power plants doesn't contribute to climate change. It doesn't have as large of an environmental footprint as any other form of baseload power. So when you think about nuclear, it provides baseload energy. That means that it's an energy source that runs very reliably, without the need for intermittence in terms of things like renewables are more of an intermittent source in terms of like solar and wind because you're only getting energy from solar and wind when the sun is shining or when the wind is blowing. Um, Nuclear power plants are also very land efficient in that you can generate a lot of energy on a very small land footprint. Um, Nuclear power also has a low ratio of the amount of energy generated to the number of, I think this ratio should actually be flipped. It should have a very high energy generation per number of workers injured. You generate a lot of power, so the numerator is very, very large, and then the number of worker injuries is very, very small. So that's a typo. That should actually say high ratio of energy generation to number of worker injuries. If you flipped the ratio, then it would be low. Very few people would get injured per unit of electricity generated from a nuclear power plant. And then nuclear power plants are big engineering projects. A lot of these nuclear power plants, like if you're a worker at a nuclear power plant, you're going to be bringing home a pretty good salary. So these Power plants are very good in terms of economically benefiting the areas where they are built, and it can do this without contributing emissions that make climate change worse. So this top plant is a nuclear power plant in Slovakia. The bottom is the Comanche generating station in Colorado, which is a coal plant. So, like, if I had to live near one of these, I would very much rather live near the nuclear power plant than I would near the coal power plant because in normal operation, the nuclear power plant, the only thing that it is producing is steam. Whereas in a coal power plant, these smokestacks, it might look the same, but it's not the same. Everything that's coming out of here is based on burning of coal. Coal burning has lots of particulate matter that gets put into the air, lots of nitrogen oxides, lots of like particulate emissions that if you breathe them in, you are there's gonna be environmental impact and environmental costs to like living near a coal plant is is much worse for human health than living near a nuclear plant because you're constantly breathing in all of the particulate emissions that this coal plant would be producing. So that's not to say that nuclear doesn't have any challenges. Every energy source has its pros and cons, but I think for nuclear, the downsides are relatively easy to manage and the upsides are very large. So then if we need to think about where we get our energy from, and we need to think about like what sources do we get our energy from, then the next thing that we should probably ask is which energy source is the safest. If we need energy and we're going to keep consuming energy regardless, then we should probably do the thought exercise to say, what forms of energy can we use such that we get our energy, but we reduce the amount of harm that we cause to society and to people and to human health from the generation of that energy. Either way, no matter what energy source you think of, people are going to end up being harmed from the use of that energy. Doesn't matter if it's solar, doesn't matter if it's coal, doesn't matter if we say, screw this, we're going to go back to, cavemen using fire for fuel. Like, fire, people are still going to get hurt by fires if that's where our energy comes from. So, really, the question that we should ask is which is the safest? And I think the way that I would the way that makes sense to me to quantify safety is to say which energy source minimizes the number of people that are harmed from the generation of that energy per unit energy extracted. So we want energy sources that in terms of that can produce a lot of energy and result in very few people being harmed from the generation of said energy. So this is showing death rates per unit of electricity production. These deaths are measured based on the deaths from accidents. So like the plant blows up or there's a big leak or the plant fails. And also the air pollution resulting from the sources that cause particulate emissions to be added to the air, which has a measurable impact on human health. And so when you look at it in this perspective, the results are relatively clear. Coal, not great. Oil, also not great. And then as you go down the list, so this is where I was saying natural gas versus coal. Like if we had to decide we're only going to get our energy from coal or we're only going to get our energy from natural gas, I would pick the natural gas because it is way less environmentally and has a way lower human cost per unit energy extracted than coal. If you compare gas to I honestly, I'm not entirely sure the difference between coal and brown coal. I imagine that it's probably similar to oil and that there's different like kind of grades of oil, and some of them are a little bit like cleaner than others. So like, but if you even if you compare gas to just whatever the standard coal is, it's about coal. The standard coal is about an order of magnitude more like deadly than natural gas is. But then if you keep going lower, hydropower is about 1.3 deaths per unit per terawatt hour of electricity generated. Wind is about 0.04, nuclear 0.03, and then solar is 0.02. So if you think about it from this perspective, it's very obvious that the best way to produce energy that would result in the fewest people being harmed from that energy is if we were to basically get all of our energy from solar, nuclear, and wind, and maybe a little bit of hydropower. Um, if you notice, like if you compare hydropower to wind, nuclear, and solar, it's about two orders of magnitude higher. And this number is kind of it, it's almost like this is kind of like an average, and this average gets skewed by the fact that there have been a couple accidents of hydropower where like a dam that is holding up a giant reservoir of water right below a giant city with like millions of people. There's been dam failures that have resulted in single accidents that have death tolls of like over 100,000 when the dam fails. So this number for hydropower is kind of skewed by some of those very severe accidents. Um, but even with those very severe accidents, hydropower is still a lot lower than any of these other kinds of energy that result in the combusting of fossil fuels, which adds particulate emissions to the air, which directly impacts human health. Um, so yeah, whenever people ask me about like how do you know what sources are safer or not, this is the kind of information that I would try to present to them. And even solar and wind, there's going to be some depth associated with that. Like if you have people installing solar panels on the tops of houses, some people are going to end up falling off of the house and breaking their neck and dying. So even solar and wind is a similar thing. If you're like a wind turbine operator and you go to the very top of that wind turbine and you're doing maintenance on it, and then that like generator catches on fire, then you're not going to have a good time. So like people are going to be harmed when they're dealing with things that are any kind of industrial endeavor that's going to have the chances of people falling. That's where a lot of the injuries at nuclear power plants come from as well. People falling from high places or big, heavy components of machinery falling on top of people that are working there. Those would be the main things that are contributing to these losses. Compared to with like the fossil fuel energy, I wouldn't be surprised if the vast majority of these are related to air pollution and not necessarily like accidents where like the plant blows up or whatever. So in terms of nuclear power, we might be asking the question like if nuclear is so great, if it's so safe, if it's so clean, why are we not building more nuclear power plants right now when we know that nuclear power is a way that we can like feed these data centers without making climate change worse and without causing as much human harm in terms of the environment as other possible sources of energy would. And with nuclear power, the main challenges are related to economics and to public perception. Um, in terms of public perception, people are scared of waste and they're scared of accidents. When nuclear accidents happen, they are very big news events. They're like they, they're scary. And when people are scared of something, it becomes harder for them to maybe think like rationally about what that thing is. It's a similar like the nuclear accidents, it's very similar to like plane crashes, where like if you compare people being transported via plane versus people being transported via car. Everybody, more or less, will get in a car and not really think twice about their being harmed by like getting into a car accident. You rarely hear of people who are like, I will not get into a car because I am concerned about the fatality rate of driving in a car. But there are a lot of people who will say that about planes. They will not get in a plane because they are worried about the plane crashing. And if you compare the likelihood of getting hurt driving a car versus the likelihood of getting hurt flying in a plane, cars are way, way more deadly, just statistically. You're much more likely to be hurt in a car accident than you are to be in a plane accident. But plane accidents are the things that like really get like if a plane crashes, it's like it's a news headline for multiple days or longer, and it's something that people like get really worked up about, even though planes are objectively safer than cars. And with nuclear power, it's kind of similar. It's also related to the fact that both with the plane and with the nuclear power station, it's something that as the public or as like a passenger, you don't really have control over this thing happening. Like if you're in a plane and the plane starts to go down, you as a passenger have no way to affect that situation. Whereas like if you're in a car and something starts to go wrong, you at least feel like you have the possibility to like swerve out of the way and avoid the accident or whatever. So there's also a lack of control element to these things. Um, in terms of the fear around them. But people also, when you talk up to them, like when you tell people that you're a nuclear engineer and that you're interested in nuclear power, they will also be worried about the waste. And so as people in the nuclear sector, in the nuclear field, we need to be conscientious of where these concerns come from. We need to be able to communicate these things to other people in a way that doesn't like that acknowledges where those concerns are coming from and doesn't like diminish them or doesn't like say, you know, your concerns are not valid. But we have to be able to communicate these in a way that also um, helps people understand how the reality of some of these things and hopefully to be able to assuage their fears because nuclear power is also very complicated. And so not everybody can understand everything that goes on with nuclear power, and you kind of have to have some of that level of knowledge to, you know, knowledge is power. And if you know more about these kinds of power plants, then you're at a better place to be able to explain where those fears come from, but you're also at a place to be able to explain, yes, you have these fears, but actually they might not be as bad as you think for reasons X, Y, and Z. So public perception is a big one. That's something that we are going to continue to have to work on as people in the industry. And economics are another. And that's mostly just around the cost required to build a new nuclear plant. Um, and so this is a chart that shows the addition of new nuclear capacity by year of initial operation in gigawatts. So from 1970, which is when we started turning on our nuclear power plants, to today, you could see that we have had a nuclear renaissance in this country before. We had a big nuclear renaissance in the 70s and going into the 80s, and that coincided with the oil crisis. And as there was concerns about oil, as there were concerns about the price of oil like skyrocketing, people decided we need to be prepared for generating energy in other forms if the price of oil can so drastically change because of like a war. So there have been booms of nuclear power in the past. And if there's been booms of nuclear power in the past, there's nothing preventing us from having booms of nuclear power in the future. But it would hopefully be not because of like geopolitical concerns, but it would be more because of we decide as a society that we want to get our energy from a different place that's going to reduce harm. And you know, maybe the economics is going to be a part of that too, where we decide like maybe we're not going to be so concerned about the short-term cost of something if the building of that project in the long term can actually be economically beneficial, even if it has a high upfront cost. Um, and so you can kind of see some trends, or at least some key points in the timeline in terms of things that have happened historically with the nuclear industry. In 1974, the NRC was created to be able to ensure the safe use of nuclear power and of radioactive materials. So like sometimes whenever you have conversations with people about like why is nuclear stagnating and what do we need to do to make nuclear power, you know, make more plants be built, some people will say like abolish the NRC, get rid of all the regulations. And I feel like if you look at this chart, you can see that that is not a very compelling argument because the NRC was created in 1974 and we had like multiple decades after that where we still built a lot of nuclear power plants. So the numbers and the amount of regulation on nuclear power, I don't think is a compelling reason for why nuclear power has stagnated. One of the things that did have a big impact was the Three Mile Island accident in the United States. That was the first major nuclear accident in the States that started to make people kind of reconsider and start to like be able to it gave people who are against nuclear power something that can point at to be able to say like this isn't safe, this is going to be bad, these are the things that could go wrong, which is kind of interesting in the sense that no person even died from Three Mile Island. So like it was bad. It cost a lot of money. But there was very negligible actual like human harm caused by the meltdown at Three Mile Island. But it was still a big event that was really scary, and that fear of another accident happening could contribute to people deciding for a while that we're going to kind of slow down our building of these plants. And then the Chernobyl accident in 1986 was the worst nuclear accident that's ever happened. A lot of people did die from the Chernobyl accident, both in the immediate accident itself and in the ensuing years of dealing with the radiation that was released from the Chernobyl accident. But, as you could see from that previous chart, even with these very high profile accidents, nuclear power still on net has very few people harmed per unit of energy extracted. So, and also the nuclear industry, to its credit, does um, it's an industry that learns, and every single time an accident has happened, we have made changes. We have learned from those accidents, and it becomes very unlikely for the same accident or the same kind of accident to happen multiple times. Like after the Chernobyl accident, which was caused by the RBMK reactors, which is a Russian design, the designs were retrofitted such that it made it much less likely for this kind of accident to ever happen again. There are still the reactor that happened at Chernobyl, the RBMK reactor, there are still RBMK reactors in operation today that have done a fine job, and it's partly because once we learned and once it became public about why the RBMK reactor failed at Chernobyl, they made design changes that made it less likely for that to happen again. Um, and then in 2011, that was kind of like things were already stagnating, and then Fukushima happened, and Fukushima was also, it was in terms of like ranking of accidents, Chernobyl was the worst, followed by Fukushima, followed by Three Mile Island. So Fukushima was very bad. Two of the reactors at the Fukushima Daiichi plant melted down and will never be able to operate again. That is a cleanup effort that is still underway, just like the cleanup with Chernobyl is a thing that's still underway. And so, yeah, if you look at after Fukushima, we have only had two new reactor installations in the United States since 2011. And that would be Watts Bar 2 and then Vogtle Unit 3. And Vogtle Unit 3 was the first AP1000s to be built in the United States. And this project was kind of it was it suffered a lot of bad management, and it suffered a lot of they basically had to keep delaying their timeline over which things were being built. They had to like reassess their design. At one point, they like poured a bunch of like nuclear grade concrete for the plant, and then they realized like, oh, it's actually not in the right spot. And so then they had to do it all over again. The Vogtle Unit 3 had a lot of issues that made it so that this thing came out way later than it was supposed to. And so we can kind of see on this chart how the public perception can like and high profile accidents can feed into the ensuing like years of what does the nuclear landscape look like. And then we could also think about the economics and realize that like if plants are taking a really long time to be built and plant builds are like going over time, over schedule, and over budget, that it makes it harder for nuclear to compete with other forms of energy that are a lot easier to get turned on. So like in terms about the waste issue, the waste is an issue that I feel like people don't fully understand like what we actually do with the waste. So what we currently do with the waste is as follows. This is at a reactor. This would be like at pretty much any traditional nuclear power plant in the United States. On site in the containment building, you would have this thing called a spent fuel pool. And so what we would do is we would at at the period of refueling, we would take our reactor, we would take the top off of the nuclear reactor so that we could see all of the fuel assemblies in the reactor. And then they use giant cranes to pick these assemblies up, and then they move them through the facility, and then they put them in this spent fuel pool. So once the fuel has been in the reactor for about 3 cycles, it will be taken out of the reactor and it will be put in the spent fuel pool. Um, the spent fuel has like the highest radioactivity right when it comes out of the reactor after being burned for several years. And so when it has the highest level of radioactivity, we put it in the spent fuel pool and we keep it there for a couple years. That time allows for the highest decaying radionuclides to decay away. Um, If you recall from your radioactivity equation, activity is proportional to the decay constant lambda times the number density of the material that you have. And so things that have a very large decay constant, recall that the decay constant is inversely proportional to the half-life. So if something has a very high decay constant, it means that it has a very small half-life. So if something has a small half-life, it means that like if the half-life is 5 seconds, then it means that every 5 seconds, half of that material is undergoing radioactive decay. And that means that you would have a lot more decays per second if something has a short half-life versus a long half-life. So after a couple of years, the things that are the most radioactive, the things with the shortest half-lives, can decay away, and we can keep this material in the spent fuel pool such that we can maintain the temperature of this fuel and make sure that like nothing melts. So it'll spend a couple years, like maybe about 5 years in the spent fuel pool, and the pool water cools it passively. And then after those radioisotopes have decayed away enough, we can then take these assemblies and put them into these dry cask storage containers. These dry cask storage containers will contain a number of spent fuel assemblies, and these sit like outside at a given nuclear facility. These things are passively cooled using air. And these casks are very well engineered. They're designed to withstand all kinds of accidents, like dropping it off of a car or having like a big car crash into it. They do a lot of testing to make sure that it's very hard for these things to break. And people like these guys here would be like doing daily monitoring of these casks to make sure that there weren't any elevated radiation levels around a cask, which would be detectable using radiation detectors and would help you make sure that like there wasn't a leak in your cask or something like that. And so these casks, they're rated at least for decades, if not like maybe like tens of decades. So this is the current way that we deal with our waste. We put it in a spent fuel pool for about 5 years, and then we can keep it in these dry cask storage containers for basically indefinitely, or until we up with a more permanent solution for where do we put our waste. Or the other thing is that, as we've talked about before, fast spectrum reactors can actually run on spent fuel. The other thing that we could do with the spent fuel is we could reprocess it. We could take these fuel assemblies out. We could do a big chemical engineering project where we extract all of the isotopes that would still be able to produce energy from us, like the remaining uranium and the remaining plutonium that's been built up. And then we can take those isotopes and make a reprocessed fuel, like a metal oxide fuel that we could then use to run our nuclear power plants. That's what France does. That would be a closed fuel cycle where once you have your spent fuel, you don't just keep it in these casks forever. You take that spent fuel after a certain amount of time and you reprocess it to get the things that you can still use out of that fuel, and then you put that back in the reactor. So we could do reprocessing, but reprocessing costs money. It's cheaper for a fuel cycle to be open, where you just let the fuel sit in these storage containers, which is why we do that in the United States. But the other thing that we've talked about is that if you have a reactor running on a fast neutron spectrum, then you can actually run fast reactors using spent fuel. Spent fuel can burn up the high actinides that are in these that are remaining in spent fuel. And so that would be there's a company called TerraPower, which has a design called Natrium. It's a sodium cooled fast reactor, and that's part of what they are trying to do. And that's part of the like one of the big advantages of fast reactors. So whenever people bring up the waste, they make it seem like it's something that there's no solution for. And it's like, actually, we do have solutions for it, but reprocessing it costs money that we don't want to do. And fast spectrum reactors are things that we've kind of not really spent the time developing, kind of for the same reason, in that, our uranium reserves are relatively strong. And so, from a cost perspective, it takes a lot of time and money and energy to develop these new kinds of reactors that maybe companies don't want to do if they can just keep doing what they're already doing, because uranium is relatively cheap and it's cheaper to do what we're currently doing than to like invest in new technologies or to invest in reprocessing. So we have solutions for the waste. It's just that those things cost money or cost effort that we have yet haven't wanted to put in. But like whenever I'm talking about climate change and whenever I'm talking about this with other people, my argument would be like in terms of responding to climate change, we need to be building new reactors. We need to be building them a lot faster than we are right now. And this method of dealing with the waste makes sense, at least for the time scales over which we need to be responding to climate change, right? Climate change is something that if we don't start getting our arms wrapped around this within the next like 50 to 100 years, then the world is going to look very different than it does today because of what climate change is going to do to the environment. And so this is a concern that we can kind of kick the dry cast can, down the road a little bit. And we can do this until we've gotten our energy situation under control. And then if we wanted to, we could, decide, all right, now we have all this spent fuel, let's reprocess it or let's burn it in fast reactors. And also the amount of spent fuel that we have is really not that much. Like, if you took all of the dry cask storage containers and all of the nuclear power plants in the United States and you put them in one place, it would occupy, like, you could fit it all in Kyle Field. And you could fit it all in Kyle Field, maybe stacked like a couple cask storage containers high. So, like, the amount of waste that we have, it might seem like it's a lot, but like space-wise, it's not really that much because nuclear is very energy dense. Um, so in terms of the economics, the thing that is kind of unfortunate is that energy generation in the US is mostly privatized. And what that means is that the people who decide what projects get built or what projects don't get built, it's dictated by people who have a lot of money, and people who have a lot of money are concerned with getting a return on their investment as soon as possible. So, like, imagine this isn't the business guy, this is Illinois energy prof, but imagine this is the business guy, and he's looking at building a nuclear plant or he's looking at building a natural gas plant, and he's deciding, I need 1,000 megawatt electric plant. The nuclear plant is going to have much higher upfront capital costs than the natural gas plant. So right off the beginning, I would have to like finance $5 billion to build the nuclear plant versus $1 billion to build the gas plant. Now, every year of operation, the fuel costs for the nuclear plant are going to be much less than the fuel costs for the gas plant because nuclear power plants, uranium is relatively cheap, and also you can use, and it's very energy dense. So the fuel costs are a lot lower than the natural gas plant. But the time to construct the nuclear plant is like 3 times longer than the time on average to construct the natural gas plant. So if you think about the fact that it's taking you longer to construct the plant, that means that it's taking longer for you to turn the plant on and then to start making the money off of the plant. So as a result of if you're borrowing a certain amount of money and then having to pay interest on that loan for a certain period of time, and it's taking you longer to be able to start getting revenue from your plant, then over the life of the loan, the interest paid to finance the nuclear power plant is much, much higher than the interest that you have to pay to finance the gas plant. So that's like the short term kind of economics of it. But also, if you were to then do the cash flow diagram and be able to say like, once my power plant has produced money, how long does it take for me to get even? It's going to take you a lot longer for the nuclear plant to break even than the natural gas plant. But once they've broken even, the nuclear power plant has a much lower fuel cost than the natural gas plant. So it's sometime after the building of this plant and then the plant breaking even, eventually, because of the lower fuel costs and because of the mostly because of the fuel cost and because of the fact that nuclear plants have very high capacity factors and because of the differences in like operating and maintenance costs, the nuclear power plant will actually be more economical than the gas plant. It just takes a lot longer to get to the point where the revenue generated from the nuclear plant kind of dwarfs the revenue, the profit generated from the nuclear plant eventually will overtake the profit generated from the natural gas plant. It just takes a lot longer to get to that point because you have higher upfront costs and it takes you longer to construct the plant. So if you think about just purely from economics, it's much more likely that somebody who's financing this project is going to build the natural gas plant instead of the nuclear plant. And so ultimately, this is a big thing that is influencing what happens like in the United States, where our energy is mostly privatized and where it's people with money who are deciding what projects get built and what projects don't. Um, Part of the reason why people are interested in small modular reactors is basically the idea that if these upfront capital costs are so high, what if we instead built a reactor that was smaller? If we built a reactor that was smaller, it would have a lower upfront capital costs, which might make it more feasible for somebody to finance the loan and for someone to pay off the loan if it doesn't cost them as much on the upfront. Um, so if we wanted to build more power plants, there's a couple things that we could do. We could have the government be more involved in the funding and the building of nuclear power plants. We have the Department of Energy. They've already built many, many nuclear power plants. So they have experience building and operating and running nuclear plants. So they have the technical capacity to be able to do it. And if the government put the money behind them, then no one has more money than the government. The government can just literally print the money if they wanted to build new plants. And if you did that, you would be able to make more plants happen. You could also just guarantee interest-free loans to companies or entities who wanted to design and build reactors themselves. If part of the issue is that people are skeptical or people are worried that they're not going to be able to get a good return on their investment, then we could just have the government foot the bill for the interest on the loan, and they could end up paying the government back on a more favorable interest scheme, which would make it more economical to build the nuclear plant. And it would be an incentive for people to build the nuclear plant instead of the gas plant. That interest-free loan idea is we're kind of already doing that, but just on a lower scale. That's what the DOE's loan program office does. It's basically like a big bank that funds energy projects, and they funded a lot of startups like X Energy. X Energy has gotten big LPO loans from the DOE. The LPO has given loans to existing plants so that they can revitalize them so that they can turn them back on instead of letting them go into decommissioning. So the Palisades nuclear power plant in Michigan is one such nuclear power plant where the DOE actually gave them money so that they could turn their reactors back on instead of letting them go into decommissioning. And then another thing is that we could probably do better with our regulatory scheme, but mostly in terms of leveling the playing field between nuclear and fossil fuels. My personal opinion is that I don't want nuclear to be deregulated because of the fact that nuclear already deals with public perception problems, and given the fact that if we have these relatively high regulations on nuclear and people are still concerned about them, then how much more concerned are people going to be if we decide we're going to cut all of the regulations on the nuclear plants, or if we're going to like drastically lower the regulations on the nuclear plants? Do we think that's going to make people more feel more safe about nuclear or less safe about nuclear? I would think it would make people feel less safe about it, and I would think that that would hurt our public perception, especially if we deregulated and then we started to see more accidents, or we started to see higher rates of radiation release. We started to see employees at these power plants getting sick because we decided to under-regulate the requirements on like how much dose somebody at a plant could receive. So I don't necessarily think that the regulations on nuclear are too high. Really, I think that the regulations on fossil fuel generations are way too low. So we probably should be regulating our fossil fuel plants higher, especially because of the fact that in their nominal operation, fossil fuel plants are burning fossil fuels, and then their waste product goes directly into the air that we all breathe, and that waste product goes directly into the air and then makes climate change worse. So it's kind of a good deal if you're a fossil fuel plant because it's like, look at these nuclear plant guys. They have to contain every single atom of waste that they produce, which costs the nuclear plant a lot of money to deal with their waste. The fossil fuel company gets to just dump that waste right into the environment, gets to make you and me and everyone else pay for it in terms of higher medical bills because of all of the health impacts of breathing in their bad air, and also because of the fact that making climate change worse means that we have worse natural disasters. It makes big floods more likely. It makes more powerful hurricanes more likely. It makes long droughts that hurt our like our agriculture sectors more likely. And guess who pays for that? You and me and everyone else, not the fossil fuel plant. The fossil fuel plant gets to basically make society pay for their externalities, and then they can just take all of that. They benefit tremendously from that on the economic side because they don't have to pay money to deal with their waste. They just put it in the atmosphere and then make all of us deal with it. So that would be, and uh public dis pu yeah, so that would be how I would kind of frame this. And again, this is just my opinion. This is not necessarily the opinion of the Texas A&M Department of Nuclear Energy or any other entities. These are my opinions. But hopefully that at least makes some sense. Um, so in terms of that's kind of like talking about the landscape and like the hype around nuclear and some of the challenges around nuclear. And now I wanted to kind of start talking more about where we nuclear power worldwide and some of the different approaches to nuclear in different countries, and also some of the newer designs that are coming into market. So the World Nuclear Association has a database that shows all of the different nuclear power in the country, where new plants are being built, and where nuclear is kind of like the largest. So as of now, there are 439 reactors operating worldwide, and there's 69 under construction. And technically, this might have changed a little bit because I haven't updated these slides since last summer. These should be relatively accurate numbers, but they might have changed a little bit over the last year. There might be like maybe less under construction if they got finished, or maybe there's more if new plants got started. But yeah, these should be relatively accurate. So this figure on the left is showing the total operating net capacity. So if you look, the United States, we still generate the most energy from nuclear power of any country in the world. Then it's France, and then it's China, and then it's Japan, and then it goes down from there. So in the United States, we get a lot of energy from nuclear power. We're also a very big country, so we consume a lot of energy. But yeah, we have more nuclear power installed than any other country. And then France is number two. And France is a much smaller country. Like if you compare the size of the US to the size of France, France is way smaller. So what it ends up meaning is that their like total percentage of nuclear, their percentage of electricity that's generated from nuclear is way higher. Ours, as we saw from that pie chart earlier, it's about 10% of our energy comes from nuclear power. In France, it's like 70% of their energy comes from nuclear power. Um, China also has a fairly large amount, but China is even like multiple factors larger population than us. They're like 3 or 4 times our population. So even though they generate quite a bit of energy from nuclear power, it makes up a smaller percentage of their overall energy makeup because their population is very big. So the figure on the left is total capacity of operating plants. The figure on the right is capacity of the reactors that are under construction. So notice that China leads basically everyone else by like a mile and a half in terms of how many power plants they have under construction. So China currently has 34,000 megawatts under construction. So if you were to take their current, 57 megawatts and you were to add 34 megawatts, then I'm bad at math, but let's see, 57 plus 34. So if you add four, then that's like 61. And then you add the three, so that's like 91. So if China gets all of this power installed, they'll be just under us in terms of how much energy they get from how much total capacity of nuclear that they have. So China's building plants really quickly. Other places are also building plants. Some places are continuing to build their plants. Some places are deciding like they want to build plants for the first time. So in lots of places, people are building new reactors, but not necessarily in the United States. So I think France is a good case study to consider and to be aware of because like when you're talking to people about nuclear power, they might like be skeptical of a country that decided we want to get a lot of our energy from power. They might say something like, what would a country look like if they got all of their energy from nuclear power? And I say it would look a lot like France. France has 57 reactors. They're all state ran, so the government runs all of their nuclear power plants by this entity called the EDF. If you look at their total energy makeup, it's like 70% of their total energy comes from nuclear. And they have a closed fuel cycle, which means that they don't just take their spent fuel and put it in those dry cask storage containers forever. They take that spent fuel and then they reprocess it into a mixed metal oxide fuel. And then they take that metal oxide fuel and they put it back in their reactors and continue to generate energy from it. So about at any given point, about 17% of France's total energy, total electricity comes from their recycled nuclear fuel. I think that that's really cool. I think that that's a model for what we probably should be working towards. Like if you look at their electricity production, it's pretty much all nuclear. They got a decent base of hydro that's relatively consistent because hydroelectric power is, as I was saying before, it's basically geographically dependent. And then their share of fossil fuel energy has actually decreased over time, and their share of renewable energy has increased over time. As a result of how France's energy makeup is done, they have, if you look at like all of the different countries in Europe, France has some of the lowest emissions and they have some of the highest air quality compared to everywhere else in Europe. They also generate so much electricity that like their electric grid is like connected with the other parts of Europe because like they're in the European Union. And they will actually they'll sell their electricity to their neighbors. So they're the largest electricity exporter in Europe, and they export about 70 terawatt hours of energy per year, just mostly from all of the like excess nuclear that they have. China is another one that's worth being somewhat aware of, given that they are currently building more plants than anybody else. Um, Part of the reason that they are building plants so quickly is because they have a large population. China has also experienced some of like the biggest changes in the standard of living of any country, maybe in history. Over the last like 30, 40 years, China has like completely transformed in terms of they've brought hundreds of millions of people out of like very abject poverty to like more middle class or at least much higher standards of living. You can see pictures of cities that looked like basically nothing was going on, like almost like agrarian villages 40 years ago are now these giant cities that look like something out of like cyberpunk or something like that. Very like futuristic looking like modern cities. They have done a really good job of increasing their standards of living. And so as people get higher standards of living, they start to expect more from the places that they live. And they start to say, we don't want to be breathing in smog all the time. We want our air to be cleaner. We want there to be less pollution. And that means that that the people living there want cleaner forms of energy. So China is doing work to address that by building nuclear power plants. They're also building a lot. They're getting a lot of energy. They're increasing their energy from renewable energies as well. Um, and so, yeah, they currently have 58 reactors, 32 are under construction. China's nuclear power is also entirely state-ran. China does it a little different than France, though, is that they have multiple like governmental entities that are instead of instead of having one entity that does everything, they have multiple entities that then compete against each other. And so these two entities will like make proposals for where they would build a plant, how much they think it would cost, and then they basically compete against each other to get contracts to then build and operate the power plants that are in China. This is a picture that I took of the Sandman plant when I went to China in 2017 for we used to do study abroad in China that was ran by Dr. Shao, and it was a really cool experience where one of the main things that we did is we toured a bunch of different nuclear plants at different stages of development. And so these reactors were the first AP1000 reactors to ever be built in the world. And this is when we were there in 2017. At this point, they had most of the facility built, and they were about to start criticality testing. So they were about to start loading in their like fuel for the first time into these reactors to start doing like the initial criticality testing. So yeah, that's a little bit about state of power and nuclear power in the world. A couple examples of other countries that do things a little bit differently than we do. This is a timeline of nuclear technology development where there's different generations of nuclear power plants. Um, this kind of started in the early 50s, where things were very much like conceptual kind of prototype reactors, where we're just starting to figure out like how can we go from the how can we actually start generating like large scale power from nuclear plants? And every generation, these plants have improved. They've increased safety, they've increased efficiency, and that is continuing to today. So going from generation three to generation three plus, that's what's like currently happening right now in the United States. The AP1000 is considered a generation three plus reactor. And then generation four is the next generation of plants that the startups are currently trying to develop right now. And so as with each generation, things are trying to become safer and more economical, trying to be more efficient and things like this. So when we talk about Gen 3 reactors, they're characterized mostly by the use of passive safety features. Passive safety allows for the reactor to be made safe and to maintain a safe configuration without the need of active control systems or active power to make certain components run. So for example, like if I go back to this picture with the AP1000s, these are the containment domes of the AP1000 reactor, and they look a little different from most containment domes. They have this little hat on the top of them, and that hat is actually a giant container of water. It's like one or maybe it's multiple like Olympic swimming pools worth of water that they keep up top. And so part of the reason that they do that, it's a passive safety feature, which is that if the plant were to lose offsite power, if somebody were to like cut these power lines and they lost electricity to power their facility, then that might stop their pumps from running. And if you don't have pumps, then you no longer have first forced circulation to flow through your reactor to keep your fuel cool. So if they were to lose on-site power, then these pools above the reactor could then be allowed to, they would open up some valves that would allow that coolant to flow downward, and that coolant would flow eventually over the nuclear reactor core and would allow for maintaining the temperature of that reactor core. And these pools are big enough that they could keep that reactor cool for, I believe it's like 48 or 72. It's like 2 or 3 days worth of time that they buy themselves by having these giant pools of water overhead. And those pools, they're just fed by gravity. It doesn't require a pump. So that's an example of like a passive safety feature. Um, they have another big thing that reactors are trying to do in terms of passive safety is to make use of natural convection, such that they basically take advantage of the natural buoyancy of the coolant and the fact that as a coolant heats up, its density decreases, and that causes it to rise. And then as that coolant cools, its density increases, which causes it to fall. So you can engineer your facilities, and also you can engineer some parts of like your reactor pressure vessel such that it gets a natural circulation flow just because of the physics of buoyancy and how the geometry and how the where the temperature gradients of your system are. And those passive safety features can allow you to make the reactor can protect the reactor during an accident, and it doesn't require on-site power. So it doesn't require a pump to be able to use natural circulation. And so passive safety features, they make your plant safer, as the name suggests, but they can also reduce the cost of your things as well, of your facilities as well. And they can reduce the complexity because it basically requires less moving parts, and it can allow you to eliminate some components as well. And then Gen 4 reactors are kind of continuing on with the Gen 3 Plus, and that they are trying to continue to incorporate passive safety features. They are trying to improve their economics through modularity and through smaller size designs. And so these are some of the Generation 4 concepts to be aware of. Gas-cooled reactors, high-temperature reactors, supercritical water-cooled reactors, sodium-cooled fast reactors. That's like the TerraPower Natrium plant that I was talking about, lead-cooled fast reactors, and molten salt reactors. And molten salt reactors are my kind of my area of expertise is with molten salt reactors because that's the project that I've been working on with Dr. Kimber. Is we are helping the Abilene Christian University is where the molten salt research reactor is being built. So that's like that's what I've been focusing on with my thesis and with all of the research I've done as a graduate student is doing different kinds of things to support the development of this molten salt reactor. So in terms of the 3 plus reactors, the Westinghouse AP1000 is the most advanced Generation 3 plus reactor that's ever been built. It's a pressurized water reactor. It has, as the name suggests, it has a power output of 1,000 megawatts electric, and it has a lot of safety systems. So it has that passive core coolant system that I was talking about before. Yeah, that allows it to passively keep the core cool for multiple days. They also use a lot of natural circulation in their design, which allows for flow to maintain through the reactor vessel, even if you have a pump failure or even if you have a loss of power that would prevent the pump from operating. In terms of some of the newer designs that are coming out, some of these Generation 4 Plus reactors, the NuScale Power Module is a SMR that this number actually might have changed. I know that at some point they decided that they were going to lower their power rating. But yeah, so this is technically an integral pressurized water reactor, and it's called an integral pressurized water reactor because you have the core, you have the steam generator, basically all in the same pressure vessel. Um, so that's part of how they're trying to make the design smaller is by packing components kind of closer together. It also makes things hopefully more economical in the sense that it requires less overall components or like it requires a smaller plant. And so that could reduce the cost on some of the things that you have to build to to make the reactor function. Um, this is the only design that's been certified for construction and operation by the NRC. So it's the only advanced like Generation 4 reactor that's actually went through the full licensing process from the NRC. The modularity means that this thing can be made in a can be made in a factory. It can be shipped in like a truck, or maybe like a ship, like a transport ship, and it could be installed directly on site. And so this is what I was saying in terms of the integral pressurized water reactor is that the core, the steam generator, and also the heat exchanger are all in the same component. Um, and this design also, if you look at this core, there's no pump. This design relies entirely on natural circulation to drive the coolant flow. So no pump means you save a lot of money on that pump, and that means that it can help make your design more economical. And it also gives you kind of peace of a peace of mind in that if you were to lose on-site power, then you would be confident that your system can still maintain cooling because it can do natural circulation without requiring that pump to operate. X Energy is another startup that's like at a pretty high technological readiness level. They are doing a high temperature gas cooled reactor called the XE100. So their working fluid is helium. They use helium instead of like as their helium is their coolant. Helium is good. It has really good heat transfer properties. Helium can operate at very high temperatures, and also helium doesn't really interact with neutrons, so that means that the helium doesn't absorb neutrons and then activate and then become something else. So you don't produce any activation products that reduces the radiation. Um, it means that the coolant doesn't get activated, which is good from like a radiation safety perspective. It means that if you have like a molten salt reactor, then the coolant has fuel within it. And that means that as that liquid fuel moves through your reactor, everything that that molten salt touches gets activated by the fission products and by things decaying. And so you don't get any of that with using helium as a working fluid. It's a thermal spectrum reactor, so they use graphite as their moderator. It has also got a very modular design, and they use something called triso fuel. So instead of having the fuel in those little like cylinders, their fuel is in these little balls that almost looks like the size. Each triso each triso ball is like about the size of a billiard ball. And within that triso fuel, there's different layers of basically different layers of materials that serve as like a containment barrier. And then in the inside, like the near the center of that core, they have these tiny little pellets of uranium of fuel. And so the triso is a kind of fuel that people are really interested in because all of those different layers give the fuel its own fission product barrier. That means that those different layers would kind of contain any of the fission products that are formed from the fission reaction in the very center of the fuel. And that means that it becomes a lot harder for those fission products to leak out, which is a good thing in terms of the radiation safety. Also, the spent fuel in uranium dioxide pellets is a lot easier to take and then do extraction. Whereas with these triso fuels, having all of the little kernels of uranium in these tiny pieces that are at the very center of this triso particle makes it such that it's a lot harder to take uh, it would be a lot harder for somebody to take a TRISO reactor, take all of that fuel, and then do reprocessing of that, which is good from like a non-proliferation perspective, and that it would be harder for somebody to take that nuclear material and then do bad things with it. Um, and they use a lot of passive safety in terms of how they deal with their decay heat. This design is configured in such a way that if the reactor were to shut down, that decay heat of the system can be passively managed through basically just natural heat transfer to the surrounding components of the system. Kairos is another startup company. They're working on a molten salt reactor that uses molten salt as the working fluid, but then it uses triso fuels as kind of like it's called a pebble, them and X Energy. It's called a pebble bed reactor, where your reactor core, instead of having all of those nuclear pellets kind of stacked on top of each other in like assemblies, their reactor core almost looks like a gumball machine where you have like this container and then you have all these balls of triso fuel that are kind of all sitting on top of each other. So that's what they mean when they call it a pebble bed reactor. And the Kairos power design is kind of an interesting molten salt reactor in that they still use a triso fuel, which means that their working fluid is a molten salt, but the molten salt doesn't have any fuel dissolved into it. The Flibe is a kind of molten salt. It is similar to water in that like it has similar thermodynamic properties to water, but it's able to go to much higher temperatures at lower pressures. So you get good thermodynamic efficiency out of Flibe, more so than you would get with water, and it allows you to operate your system at lower pressure, which means that it allows you to make your design less you have less engineering that goes into your design in terms of like you need a small if you're at high pressure, that means that you need a very large reactor pressure vessel with like a very thick steel containment to be able to contain the pressure of the high pressure like water. Whereas if you operate at low pressure, then you can get away with a much smaller, like maybe a couple centimeter pressure vessel. And if that means that you have to use less nuclear grade steel, then that means that your design can be cheaper. If you have to use lower pressure and therefore smaller thicknesses of your components in your system. It is also a thermal spectrum reactor. It also uses a graphite core, it uses graphite as its moderator. Um, and they are able to passively cool the reactor using a combination of natural circulation as well as probably decay, it, heat transfer to the surrounding environment. So yeah, that the Kairos molten salt reactor is different than the Abilene molten salt reactor that I've been working on, in that the Abilene molten salt reactor uses the fuel is dissolved within the coolant, and so that fuel salt, if you will flow like through the entire primary circuit, whereas their fuel is all contained within the pebble bed core, and then they just use molten salt as a working fluid. Um, so that's just a couple of the like designs that are out there. That's not an exhaustive like discussion of those designs, but it hopefully helps you start to understand that through what we've talked about in this class, you have like, and we've focused on like thermal spectrum power reactors using water as the working fluid. We talk about it that way because those are the designs that you're most likely to see if you go into the workforce and like go work at a nuclear power plant right now. But hopefully, you're starting to see that even if I go from the light water reactor to a molten salt reactor or to a gas cooled reactor, that all of the fundamentals are still the same. And so most, if not everything that we've learned for light water reactors, there's knowledge that you can draw from to be able to understand. Once you can understand a light water reactor, you can understand these different kinds of reactor designs. Just like once you learn MATLAB, you can learn Python, you can learn another scripting language. Once you learn kind of the neutronics and the fundamental nuclear physics for a light water reactor, you can take that information and translate it into other designs. Um, these designs of these nuclear reactors, they're complicated systems. They have a lot of variables that are coupled together. You have not just your heat generation in your core, but you have how the mechanics of that system are put together. You have how are all of your individual components linked together. You have what are the geometry of those things. You have the heat transfer that's involved with taking your heat and from your reactor and moving it from place to place to convert that thermal energy eventually into mechanical energy, into electrical energy, and into power. And you have fluid flowing through these things. So to really design a nuclear reactor, you need to know a lot of things. You need people who you need a team of people that have a lot of different skill sets. You need somebody who can design the reactor core. You need or a team of people who can design the reactor core. You need people that understand fluid flow um, and coolant properties. You need people who know heat transfer as well, so that you can design your heat exchangers and your other components of your reactor that are required to take that heat energy, move it somewhere else, and to do it in a safe and efficient way. And a lot of these components and their variables are coupled. Like we know that our power generation will affect our temperature. We know our temperature will affect our cross sections. We know that our cross sections will affect our flux, which will affect the power. The temperature of things ends up affecting our materials. It ends up influencing what happens to our materials. Same thing with the radiation and the flux in the reactor. That'll influence our materials. The kind of reactor that we pick and how we set up our core will impact aspects of not only what happens, how the reactor runs, but also it affect how those materials evolve with time. So you can think of these nuclear power plants as like these big thermodynamic systems where you are taking heat from fission, using these components to move it and convert it eventually into a useful form like of electricity. So in nuclear reactor design in this course, we mostly focus on neutronics. You can use your neutronics to find your flux distribution and your power generation. Once you know how your power is distributed and how your temperature is distributed, you could do CFD or other kinds of analyses to understand what does the fluid flow through my reactor look like? How could I optimize my fluid flow so that I get the most efficient heat removal from my system and so that I don't end up like overheating any parts of my reactor. You could then use your knowledge from like heat transfer to design the thermodynamic components that would be involved with making this big system that can convert that heat into electricity. And so those are the things that you'll kind of start to focus on the next year of your courses with like senior design and also with the electives that are offered in your senior year. So I really hope that you enjoyed this course. I hope that it gives you a better understanding of how and why nuclear reactors work, how they do what they do, an appreciation for the field that we're deciding to embark in, and a deeper understanding of the things that we need to be concerned with as nuclear engineers. I think that you guys are in a really good place in terms of like your future in the nuclear field. I think is very bright. I think it's a very interesting and exciting time to be involved with nuclear engineering. About the number of opportunities that there are right now compared to when I was finishing undergrad are a lot better, bigger, and better. So potentials for like finding jobs and being able to do cool stuff right out of undergrad is high with these startups because startups need people. And if you go to a startup, you could get your hands into like a lot of different baskets in terms of being able to understand and figure out like what your niche is. You could figure out like if you want to be a neutronics person, or if you want to be like a thermal hydraulics person, or if you want to be like a radiation safety person or a materials person. So you've kind of gotten to the point where you have all of your fundamental knowledge, and then in your senior year, you're going to start applying it and start figuring out like what is the thing that you actually want to focus on. So keep that in mind, like when you're going into senior design and thinking about what your role in your senior design project is going to be. Also keep in mind, like when you're doing senior design, what's a cool project that you think would be fun? And you can kind of use that to leverage. You can use your senior design project as a way to leverage where you end up working. So you would want to keep those things in mind as you're going into your next year. You would also want to start thinking about just like in general, because you're about to be graduating, like where would you want to work? Where would you want to live? Would you want to live in a city? Would you want to live would you want to be working at a startup? Would you want to be working like at a nuclear power plant that might be like not in a city, but maybe like, in a more rural area? Um, and keep those things in mind too when you're deciding like what other courses you take in your senior year. Like you could take the new in 418, which is the core design class, which will help you, that'll help you learn how to use industry standard core modeling programs to do detailed reactor design, much more detailed than like our reactor design project. If you want to learn about CFD and nuclear thermal hydraulics, If it's offered, I would highly recommend. 418 is a great class. Newen 428, which is the CFD class, is also really good. It'll give you an intro to using CFD tools to be able to predict things like flow distributions in complicated systems. Also, Newen 430 is like a it's like numerical methods in scientific computing applied to nuclear engineering. So that could give you that's a good class to improve your programming skills and to be able to apply your programming skills specifically to nuclear focused applications. And so keep those things in mind. Start thinking about what you want to do next year. And start thinking about what you want to do for your career. If you have any questions about any of that, in terms of like, advising or guidance in terms of what courses might be good for like what you want to do, feel free to let me know. And yeah, I wish you all the best of luck. Thank you for being in my class, and yeah, keep in touch, and I'm excited to see what you guys are able to accomplish. So yeah, that's the end of our lesson for today. Thank you for your time. If y'all have any questions, feel free to let me know. And also, if you wouldn't mind, please complete those course evaluations and make sure that you complete the quiz that I'm going to post for today as well. Thank you and take care.